Hello and welcome to my YouTube channel. In this presentation, we are going to talk about energy bands in semiconductors. So without any delay, let's start the video. The first question that should come to our mind is what is energy band and why they are important in case of solids. So before jumping into the energy bands, let us first discuss about solids. Solids are nothing but they are a state of matter, just like liquid and gas. Now coming to the matters, matters are nothing but collection of atoms. And if we further divide or go deeper into the atoms, then atoms are nothing but they are comprised of positive nucleus and negative electrons. So basically collection of atoms becomes matter, and there are three types of matters in nature that are solid, liquid and gas. Now motion of electrons and other constituents atoms are governed by the laws of quantum mechanics. So we are going to briefly enter into the quantum world to understand the motion of electrons, and using the quantum physics we will understand how these energy bands are basically developed. Okay, so to understand quantum mechanics we have to take the help of Schrodinger equation, because using this equation we can explore the fundamental movements of constituents of an atom. Now it is very difficult to go deep into the Schrodinger's equation, but in case of small understanding, or if you have to have a brief understanding of quantum mechanics or Schrodinger equation, then you can use this link provided in the presentation. So if you go to this link, you can see how the Schrodinger equation is developed and how the wave equations are generally behaved in nature. But I am not going deep into this physics, rather we are interested in how the quantum physics actually helps us to understand the formation of energy bands in solids. So let us continue. So Schrodinger equation was basically derived by Erwin Schrodinger in the year 1925. So what this equation defines? This equation defines a wave function. So remember the word wave function. So the function is more or less like a wave. We will see how or why this function is called wave function. So basically Schrodinger equation defines a wave function of a particle, and that particle can be electron or any other particle which follows the rule of Schrodinger equation, and they have certain value at every point in space for a given time. So these particles will always have a certain value of energy at a point in space at every given time. The wave function is nothing but it can be a number of different states at once. So Schrodinger equation is used to derive the behavior of particles or group of particles which may have different states at once. That means they can have multiple states at a very particular time. For example, what are the behaviors or what are the different states? So these particles may have different positions, they can have different energies, they can have different velocities or other physical properties at the same time. That means if we go by Schrodinger equation, then these particles can be present at two places at once. That means using Schrodinger equation we can prove that an electron is present at two places at the same time. Now let us briefly derive the equation. I'm not going very deep into the Schrodinger equation. Rather, we will be discussing this only from the surface level so that we can understand how the energy bands are derived. Schrodinger equation basically is given by the wave function of Hamiltonian energy operator H and the energy of wave. So according to which Hamiltonian energy operator is equal to the energy of wave. So the electrons or particles can behave like a wave, where H is nothing but the total energy of the system. When we say a system, it may be a particle or it may be a group of particles. Now, H, this energy is given by the sum of kinetic and potential energy of that particular particle. So Ke is representing the kinetic energy of the particle and Pe is representing the potential energy of the particle. Now, if I substitute the value of potential energy in this equation, then it is given by H is equal to P square upon 2m plus V, where P is nothing but the momentum of the particle, m is representing the mass of the particle, for example mass of the electron, and V is the potential energy associated with that particle. So the energy is the sum of kinetic energy and potential energy. Now if we substitute this equation in the above equation, okay, then we will get the function H is equal to minus of H square del square upon 2m plus V, where P or the momentum is nothing but imaginary part of the mass of particle multiplied by the reduced Planck constant. Remember, H is your Planck constant, H dash is your reduced Planck constant. Okay, so here we have the Planck constant H and here we have the reduced Planck constant, which is represented something like this. Okay, so if we substitute all this value of H in the above equation, then we will end up with minus of H square L square upon 2m plus V multiplied by the wave function is nothing but the energy of wave multiplied by wave function. Now if we reshuffle or rearrange this equation, we may get the final equation for Schrodinger given by del square multiplied by wave function plus 2 into mass of the particle divided by the reduced Planck constants square multiplied by energy minus potential energy multiplied by the wave function is always equal to 0. Now the question comes, why are we deriving this equation and what we can depict from this particular equation? So we can say in short, this equation states that for every given potential energy V, okay, every given potential energy V, we can find an energy eigenvalue E which gives the particle's energy under consideration. So please remember, this is the statement for the equation derived. That means for every given potential energy or potential energies variation V, we can find energy eigenvalue E which gives particles energy under consideration. Let us move ahead with the Schrodinger equation. Let us take a very simple example with a very basic particle, that is our hydrogen, which has got only one electron. So the potential energy of hydrogen atom is given by Q1 into Q2 upon R, where if we substitute Q1 and Q2 to be electrons, then it will be E square upon R. So this minus is representing the charge of electron. Okay, so V, the potential energy, is given by minus E square upon R. If we go with CGS system, centimeter, okay, system, in that case, centimeter gram second system, in that case, potential energy V is given by minus E square divided by 4 pi epsilon mod of R, or we can say absolute value of the R. This equation is very important when we have to derive when we have to understand the behavior of electrons or the energy associated with the electrons in any particular matter. Now, substituting the value of V in the Schrodinger equation, which was derived the previous slide, we can end up with the energy eigenvalues of hydrogen atom, that is given by En, which is equal to minus me to the power 4 divided by 8 into epsilon square h square upon 1 upon n square, where this n can be 1, 2, 3 and so on. And these are called principal quantum number. They cannot be 1.2 or 2.3 or something like that. They have to be always 1, 2, 3, or we can say complete numbers. So substituting these values of n, we can find the value of energy eigen value of the atom. So suppose if we substitute n equal to 1, okay, then we may end up with En equal to minus 13.6, because m is constant, mass of electron, E is constant, charge of electron, 8 is constant, epsilon is constant, Planck's constant is constant. So all these terms are constant, and if you substitute appropriate values, you will get minus 13.6 multiplied by 1 upon n square electron volt. These are the energy associated with the particles at different energy locations, or these n are representing the energies which are associated with those energy levels which are associated with those particles, also known as principal quantum number. Now let us try to understand or visualize this discrete energy levels of an atom. Let me simplify that equation and let me briefly tell you how this equation helps us to understand the behavior of energies associated with the particles. For example, if we have different values of n can be 1, 2, 3, 4, 5 and so on, then if we try to get the value of En or eigen value, then the energy levels will look like this. So if you substitute 1, you will get minus 13.6 electron volt. If you substitute n equal to 2, you will get minus 3.4 electron volt, and so on. If you go on increasing the value, you can see the gap, okay, the energy levels gap is decreasing as we go higher and higher in terms of energy level. Okay, so if you go for infinite value n, if you substitute n equal to infinity, then you will reach to a state called free state, or you can call it vacuum state, where you will end up with the final energy value to be 0 electron volt. So remember, here few things that we can observe is that we are starting from minus 13.6 electron volt when n is equal to 1, and if we reach to infinity, we will get 0 electron volt. So basically we are moving from negative value towards 0. Okay, how can we correlate these numbers with the electrons or the atoms that we study? So here we have the ground state of hydrogen atom, and here we have the vacuum state. So when we started talking about the atoms in general, then in our school days we have studied that an atom comprises of a nucleus around which the electrons are orbiting. These electrons generally have a particular energy associated to them, and that depends on the orbit in which these electrons are rotating. For example, if we take the periodic table, row 1 has got 1s, row 2 has 2s 2p, row 3 has 3s 3p, row 4 has 4s 3d 4p, and so on. So keep an eye on these values of row and associated values of the electrons. Okay, so in S you can have only 2 electrons maximum, in P you can have 6, and so on. Now if we correlate, then the lowest energy is at this point where you have row 1 1s. Highest energy is associated when you move upward towards the orbits, or row 6, row 7, and so on. If you correlate, so this is the basic diagram of an atom. Then we can subdivide the energies associated with the electrons based on their positions in the orbit. For example, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. And similarly, if we bring that energy using the Schrodinger's equation, then the energy associated with those electrons can be visualized in this fashion. So if you are at lower energy level, you have very high energy difference. As you move higher and higher in the energy level, the difference becomes less and less. Remember, we move from negative to maximum zero energy level. Now, these are the energy levels when we have individual atoms. Now assume if we bring 2 or more atoms close to each other. In that case, what will happen? So we know that solids are matters in which atoms are very densely packed, whereas in gases, the atoms are not that densely packed. Okay, so solids have atoms which are very densely packed. They are very close to each other. So the interatomic distance, okay, in these atoms are in the range of few Armstrong, or few Armstrong to few micrometers. So they are very close to each other in this range, Armstrong to micrometer. So what will happen when these atoms come very close to each other? Then the outermost orbits of these electrons start interacting with each other, and that causes the behavior of linear combination of atomic orbits. So when two atoms are spaced very far from each other, their electromagnetic field do not affect each other. So every atom has nucleus around which you have the electrons rotating out. And when the electrons are rotating, these electrons in motion generates an electromagnetic wave. Okay, and these electromagnetic field around the atom do not affect each other if these atoms are placed very far from each other. But when we bring these atoms very close to each other, then the electromagnetic field around each atom starts influencing the nearby atoms, and that will cause the linear combination of atomic orbitals. So if we keep bringing these atoms closer and closer, the outer orbits electrons, okay, of the individual atoms start influencing the nearby electrons of the nearby atoms. Due to close proximity to other atoms, these energy levels associated with the atoms start spreading away. So this concept is again a very important concept, that the energy levels which we discussed in the previous slide starts spreading away. How can we visualize that? In that case, So for example, this x-axis represents interatomic distance in Armstrong unit. So you have 0 Armstrong, 1 Armstrong, 2 Armstrong. So if the atoms are kept very far, then suppose you have atoms like this. So one atom is here, one atom is here. So they are very far and they are farther than 13 Armstrong. In such case, the atoms are not going to affect each other. But what will happen if we start bringing these atoms close to each other like this? In such case, what will happen? Because now the electrons at the outermost orbit may start influencing each other due to their electromagnetic field. And how can we visualize that? So suppose we have one atom with a nucleus N. In that case, we saw that the energy levels are in discrete level, and as we go higher and higher, the energy levels come closer. Okay, and in the lower you have very large gap between the energies, but as we go higher, the energy gap becomes very small. Now when we bring another atom very close to the first atom, then the outermost electrons of the two atoms will start influencing each other, and that will cause spreading of energies at the higher energy levels, and this is how the spreading takes place. So this is about two atoms, but if suppose we bring more and more atoms close to each other, which is in the case of solids, then these energy levels start spreading each other, and they may look like this. Remember, here still the energy levels are discrete, they are not continuous, they are discretely placed but very close to each other due to interatomic interactions. Now these are the individual atoms allowed energy states. Within this band, you have the energy which are allowed for the atoms. Remember, when individual atoms are very far from each other, their energy levels are discrete and they do not influence each other. But when we bring more and more atoms close to each other, their energy level starts spreading away, and the electrons at the outer orbits of the atoms are more affected compared to the electrons in the inner orbit. So here you will find more interactions, because there we have the higher outermost electrons. Okay. Now, furthermore, if we want to simplify this diagram, then again we can start with the interatomic distance versus bonded energy, and one atom will have energy band which is given by E1, E2 and so on, E3, E4, E5. But when we bring all these atoms very close to each other, these energy bands remain in this discrete level, but they spread like this function. Now the question comes, how can we visualize these energy bands? Because the lower energy band or the lower energy section in the E5 is overlapping the higher energy section of the E4. These are energy bands. So we can simplify this and we can draw this like the one which is represented in the presentation. So individual atoms energy states are represented like this. When there are lots and lots of atoms which are bonded very close to each other. And now we can segregate these energy levels in two bands. One is our conduction band, which is higher energy band, and valence band, which is our lower energy band. This gives rise to our bands or energy bands in solid devices. So here these are generally represented in the books like this, two square boxes which are having valence and conduction band. Valence band have less energy compared to conduction band, and the gap between these two are called energy band gap. So this is how we started the journey from simple atom with electrons orbiting around it to the conduction and energy valence band. Okay. Now let us go ahead and try to understand or realize what actually it means. So we have studied there are three different types of solids. One are called metals, okay, good conductors. Then we have semiconductors. Then we have insulators. So at 0 degree Kelvin, semiconductors have the same structure as insulators. So at 0 degree Kelvin or at very low temperature, semiconductors are basically insulators. They behave just like insulators. They do not allow or they do not conduct electricity. So in that case, no current will flow from the semiconductor even when we apply external electric field by using battery or any other electric field. But when we bring these semiconductor at room temperature, okay, when you move it to a higher temperature, the electrons in the semiconductor gets excited because of thermal energy and they can cross the forbidden energy gap. Okay, and that may give you the rise of current or electrical current in the semiconductors. So at room temperature, electrons in the semiconductor gets excited due to thermal energy, and then using that you can make the currents flow. So in general, we have metals in which the energy band or energy band gap is 0. Okay, so they are overlapping each other. Whereas in semiconductors, we have a small energy band gap. Okay, and if we provide external electric field, the electrons from the valence band can jump to the conduction band, giving rise to current. And third type is our insulators, where the energy band gap is very large. So of course, you can make the current flow in insulators also, provided you have to provide very large potential or very high electric field to make these electrons jump to the conduction band, and that depends on the value of Eg or energy band gap. Now these energy band gap for germanium stands at 0.67 electron volt, and for silicon is 1.1 electron volt. Case of gallium arsenide, which is a compound of semiconductors, in that case the energy band gap is 1.42 electron volt, and for diamond this energy band gap is 5 electron volt. So remember, the highest energy band which is completely filled is called valence band, and the next energy band is called conduction band. So valence band are mostly completely filled, and the next to that is our conduction band. Electrons can move from valence band to conduction band if we can provide an energy which is greater than Eg. We will discuss these things in the upcoming presentations. Remember, conduction bands are generally empty or partially full. They are not fully full. Okay, they are not totally completely filled. They are partially filled or mostly they are empty. With this, I would like to end the presentation. If you have any doubts or suggestion, please share your doubts and suggestions in the comment section. And if you have not subscribed my channel, then I would request you to please subscribe the channel and share the videos with your friends or colleagues. Thank you very much and have a nice day.